Okay, I have a discharging capacitor here. I know it's discharging because it says that it's been previously charged with a battery with a potential of 12 volts. That means that V is equal to 12 volts. That'll be important later. First, I want to know just how long does it take the circuit to completely discharge? So there's two steps to this. First, you need to find the time constant. The time constant is equal to R times C. R is 2 mega ohms, C is 3 microfarads, 2 times 10 to the 6 ohms, 3 times 10 to the minus 6 farads. Those cancel out, and so that leaves me with 6 seconds. So that means that the total time is 10 times the time constant. So that's going to be 10 times 6 or 60 seconds. That's the answer. And then the second part, I want to know how long does it take for it to reach a charge of 20 microcoulombs. So we want to look at the the equations for a discharging charge is going to be this, Q e to the minus t over RC. And so Q is equal to big Q times e to the minus t over RC. Now, big Q is equal to C times V. That's 3 microfarads times 12 volts, which is equal to 36 microcoulombs. So Q, little q is 20 microcoulombs, 36 microcoulombs, that's the total, the maximum charge, times e to the minus t over RC. I've already found RC, it's equal to 6. So I can solve this. I get 20 over 36 equals e to the minus t over 6. To get rid of that exponential, I have to take the natural log of both sides. That cancels that out and leaves me with negative t divided by 6. The natural log of 20 over over 36. That's equal to negative 0.58. And then I just multiply that times 6 to find the total time. I get 3.5 seconds. So t is equal to 3.5 seconds. That's the answer there. That makes sense, right? Because the time, yeah, that's reasonable for us to reach that charge of 20 microcoulombs. Because I know the total charge is 36 microcoulombs. It's definitely less than this 60 seconds. At one time constant, we're at about 67% fully charged. So yeah, that's reasonable. All right, here I have a positively charged particle and there's a 2 Tesla magnetic field. That's B is equal to 2 Tesla. Uh, the particle has a speed equal to 8 meters per second. And then when in the magnetic field, it moves with this radius of 4 meters. Here I want to know just what is the direction that the particle will initially travel. That is, what is the direction of the force? I know it's not in the x or the y-axis. It has to be either plus or minus z. Let my index finger go in the direction of V. Magnetic field is my middle finger, and so that's going to be in the plus Z direction or out of page. Both of those are correct, just different ways of saying the same thing. And then what is the mass to charge ratio? I know from the cyclotron equation, which is on your equation sheet, that R is equal to mv over qb. I just want to solve for the mass to charge ratio. That would be RB over V. R is 4 meters. B is 2 Tesla. By the way, these are not really physical numbers. I just made them so that they're easier. 8 meters per second. In this case, my mass to charge ratio is 1. That's in kilograms to coulombs. So that's the mass to charge ratio for that spectrometer, that cyclotron. Here, I want you to draw the light rays as they go into these different media. So based on these numbers, I can say that it's going fast here. Then it moves more slowly because the index of refraction goes up, and then it's moving fast here. Imagine my wave fronts. If it slows down here, that means it's going to bend towards the normal, and then here as it moves into this new This new medium is moving faster. It's going to bend away from the normal. In fact, it's going to bend more away from the normal than it is up here. So I know that this angle right here, because this index of refraction is smaller, that this angle must be bigger than that angle. All right, which gives me, that's the first part. For part B, I want to know the angle of that light ray in that third medium. So I'd say 1.2 sine of 40 is equal to 1.1 sine of theta 3, and then I'd solve that for theta 3. The inverse sine of 1.2 sine 40 divided by 1.1, and that's equal to 45 degrees, which jives with what I think it should be, that it should be bigger than that first angle. And then finally, what is the direction of magnitude? I have this proton. Remember, proton is plus 1.6 times 10 to the minus 19 coulombs. That's the fundamental unit of charge. That says 1e on your, that's the fundamental unit of charge E on your equation sheet. I want to know the direction of magnitude of the magnetic field at this location. So for part A, the magnetic field is, gosh, I always forget what it is this mu naught I over 2 pi r. Mu naught I over 2 pi r. That's going to be 4 pi times 10 to the minus 7. I is the current in the wire, that's 2 amps, given right here, divided by 2 pi, and then R is 0.3, yeah, 0.3 meters. That's just the distance from here to where your charge is located. Notice the pi's cancel. I'll get rid of that 2 as well. And that gives me a magnetic field equal to 1.3 times 10 to the minus 6 Tesla. All right, I need to know the direction too. I'm going to do my right-hand rule with my thumb in the direction of the current. Then my fingers wrap around into the page, and then on this side out of the page. So that's in the plus Z, or out of the page direction. And then for part B, I want to know what is the magnitude and direction of the magnetic force. So F is equal to QVB sine theta. In this case, the angle theta is 90, so that's going to be equal to 1. Sine of 90 is equal to 1. Q is 1.6 times 10 to the minus 19 coulombs. It's that proton, so I know the charge. It's the fundamental unit of charge. V is 6 times 10 to the 5th meters per second. And then B is what I just found, 1.3 times 10 to the minus 6 Tesla. And then that gives me a force of 1.2 times 10 to the minus 19 newtons. And then the direction of that force, well, I have a velocity that's up, a magnetic field that is out of the page, that's B. So if I do my right-hand rule, that gives me a force that is in that direction. So it's in the plus X or to the right. Either one would be correct. All right, let's move on to the multiple choice then. So which of these statements about a household circuit is true? The circuit breaker turns off if IN exceeds I out. No, that would be true for GFCI, but not for that. The GFCI contains an ammeter. Yeah, because it's monitoring the incoming and the outgoing current, so it has a very sensitive ammeter. That's why they fail sometimes. That's why you have to test them to make sure the ammeter still works. As you add more devices to a household circuit, the voltage to each device increases. No. In fact, the voltage will always be the same because they're in parallel. And then the grounding of your house protects you from faulty devices. Yes, remember, if you have a fault inside of your device, the grounding gives you an alternate path to ground. So it looks like 2 and 4 are A. On a circuit breaker, you have these circuits, or these devices, and then I add this other device. Now remember, I is equal to P divided by V. That was just my power equation, P equals VI, and I solve it for I. And for all of these, V is equal to 120 volts. So I can calculate the current for each of these, like 1200 divided by 120, that's 10 amps. 60 divided by 120, that's 0.5 amps. And then 240 divided by 120, that's 2 amps. So this is working just fine at 12.5 amps. But I add this 180 watt, 180 divided by 120, that's 1.5 amps. So somewhere between 12 and a half and I add, that's plus that would give me 14 amps, somewhere between 12.5 and 14 amps. It kicks off, and the only number in between there is that 13. All right, which of these graphs represents the current versus time? This is a charging capacitor. Like when I close this switch, it causes the capacitor to charge. So let's look at our equation sheet. The current for a charging capacitor, well, good news is it doesn't matter if it's charging or discharging because the current is always an exponential decay function, and an exponential decay function looks like that for number 3. Consider this circuit. What is the charge on the capacitor after t equals 5 seconds? This is a charging capacitor. Now let's look back at our equation sheet. The charge on that charging capacitor looks like this. It's that exponential growth function. So Q is equal to big Q, which is C times V, that's 32 microcoulombs, times 1 minus e to the minus t, which is 5, divided by RC, which is 4 times 2, or 8. And then if I put those in, I find that the answer is 15 microcoulombs. All right, that's A. Proton is traveling at 2 times 10 to the 6. That's its velocity in a magnetic field that is 3 Tesla. What is the magnitude of the force? Okay, so F is equal to QVB. Oh, it's a proton, so I know that Q is 1.6 times 10 to the minus 19 coulombs. That's my fundamental unit of charge. Let me just remind you where that is. I've mentioned it several times. That is this value. That is the charge on a proton and on an electron. V is 2 times 10 to the 6, and then B was 3 Tesla, so that gives me 9.6 times 10 to the minus 13. That's right, number 5 is C. Wire carries a current of 2 amps in a direction that makes an angle of 20 degrees with a magnetic field that is 0.5 Tesla, and I want to know what is the magnetic force on a 5-meter length of the wire. So L is equal to 5 meters. Remember, F is equal to ILB sine theta. I put in each of those values. I find that F is equal to 1.7 newtons. Magnetic field distance. What is the Oh, I give you the magnetic field and I want to know the current. So let's look back at that equation sheet. Remember, there are 2 equations here that look a lot alike. There's this one, and then there's this one. This first one is for a long straight wire, and then this one is for a coil of wire. And I can tell the difference because this one has an N in it. N is for the number of turns. So it's this first one, mu naught I over 2 pi r. B is equal to mu naught I over 2 pi r. And I'm looking for the current, so I'm just going to solve it for current. B 2 pi r over mu naught. B is 2 times 10 to the minus 5. 2 pi r is the distance from it, that's 0.02, divided by 4 pi times 10 to the minus 7. I know, so my pi's can cancel. I can cancel that with 2 down there. That cancels there. 0.02 times 10 to the minus 0.02 times 10 to the 2. Yeah, so C is the right answer for number 7. Number 8, which of these statements is true? Iron can be magnetized. Sure, iron is ferromagnetic. It doesn't have to be magnetic, but it can be magnetized. Magnetic fields are directed from the north to the south pole. That's not true. Magnets repel ferromagnetic materials. Actually, no. They can, like a ferromagnetic material can be magnetic, and a magnet, the right pole will repel it, but not necessarily. So C is the right answer. What's the direction of the force on this particle? So it's our right-hand rule. Let our index finger go in the direction of V. Our middle finger goes in the direction of B, which is into the page, and that gives me a force that is down, D. Positive ion, that's called a cation, travels in the minus X direction. So that's my V through a vacuum in a region where the magnetic field is in that direction. Uh, so that gives me A into the page. The force is into the page. Positive particle approaches the current carrying wire. What is the direction the particle will go? So first we want to figure out what is the magnetic field. It's into the page on this side and out of the page on this side. I use my third application of the right-hand rule, and my thumb go in the direction of I, my fingers wrap around, and then I have my index finger in the direction of V. My middle finger goes in the direction of the magnetic field, so my force is, looks like, to the left. So number 11 is A. Here I have this mass spectrometer of particles traveling through this magnetic field, and I want to know the direction that will travel. I actually had this same question a few questions earlier, so hopefully you got it right there and here. It's just a different context. So let my index finger go in the direction of V. Magnetic field is into the page. The force is down. That means it's going to travel in that direction. So down is the right answer. Which of these statements is true about a mass spectrometer? The magnetic force increases its kinetic energy? No. Remember, the magnetic force is a centripetal force. It does nothing to change the magnitude of the speed, only the direction. The mass spectrometer can determine the mass of the particle. No, that's not true either. It can determine the mass charge ratio of the particle, but not the mass. And then the magnetic force acts as a centripetal force. That is true. QVB is equal to mv squared over r. In fact, that's where we get that equation, the cyclotron equation. This is just if you're interested. If I solve this for m over q or r or whatever, see those v's cancel, I'll just solve it for r. It's mv over qb. That's where we get that cyclotron equation. We'll need that here, actually. Here I have this magnetic field of 3 Tesla, the velocity of 4 meters per second, and a radius of 2 meters. What is the particle? So I can calculate the mass to charge ratio, m over q, is what, RB over V. I'm just solving this equation for M over Q. And then that's going to be R is 2 times 3 divided by 4. 6 divided by 4 are 3 halves. That's my mass to charge ratio. Uh, this has a 1 to 3, 6 to 2, 2 to 12. So this one is a 3 halves ratio. That's Micah Light. By the way, this is my family. My daughter is Ada. She's 17. My wife, Kaisa, she's what? She's 46. Me, that's gonna be 49. Y'all don't need all my ages, I guess. This is my son, Micah, though he has an H in his name, like the prophet, not the mineral. Anyway, that was TMI, I suppose. What of the following statements is true? Newton believed light was a particle because of refraction? No, he believed it was a particle because of reflection. Huygens believed light was a wave because of reflection? No, because of refraction, he believed light was a wave. Einstein showed light was a particle through the photoelectric effect. That's true. And Young showed light was a wave through the double slit experiment, so that's not true. Double slit, we haven't talked about this, but you should have known that Young showed that light was a wave, not a particle. The double slit experiment showed interference. All right, which of these appropriate list photons in order of energy from least to greatest? Okay, so looking at these, I know that radio has the least. That gets rid of these, and X-rays has the greatest. Okay, so it's just ultraviolet and infrared. Well, infrared is a lower energy, so C is the right answer. What is the angle here? Well, this angle is 50 degrees. That means that this angle is 90 minus 50 or 40 degrees. And 40 plus 120, that's equal to 160. That means that this is 180 minus 160 or 20 degrees, which means this is 70 degrees. So this is also 70 degrees. Light travels from medium 1 to medium 2. Looks like it's slowing and it's fast here. The index of refraction is greater where the speed is slower, so medium 2 is the right answer. And then light travels through air. Sorry, what is the angle of the light ray? Okay, yeah, so traveling through air, that's n equal 1, and this is n equal 1.3. This angle is 40 degrees, and I want to know what is this angle. I know it's going to move closer. So I could get rid of that answer. In fact, I could probably get rid of A and C too. Those just, it's not going to move that much. It has to be either B or D. And so I say 1 sine of 40 equals 1.3 sine of theta. And if I do that, I find that the answer is theta is equal to 30 degrees. All right. And then finally here, what must the angle be for total internal reflection? I'm moving here from a low to a high index, but total internal reflection does not occur. Now, if I try doing the calculation, 1.3 sine of theta, this would be my theta critical in this case, is equal to 1.4 sine of 90. That's the special case where I get total internal reflection. Then when you tried to calculate this, you would get an error in your calculator, and that's why that physically it just doesn't occur, that you don't get total internal reflection. So mathematically it doesn't work out either. All right.